Okay, so as you may have seen, I failed to solve the problem last night. Um, then I stayed up way too late dealing with stuff. Then I woke up this morning and spent probably another, I would say, 2 hours on it and got to a solution. And unfortunately, I was doing a bunch of other stuff, popping in and out, stopping and starting, so I didn't film it, which is too bad because it might have been educational but very long. But anyway, I'll walk you through the solution and I'll add comments as I do it so you can understand it. So if you remember correctly, it gives us a bunch of tiles, okay? And it says each of these is a tile from a camera and they get glued together by, having to match on the right and left side and or top and bottom, whatever. This, if I put this one next to that one, this column has to match that column. So and in part one, they say, rotate, flip, and rearrange them to find a square where they all line up. And then you want to find the IDs of the four corner tiles together, okay? And so it turns out for part one, the easiest way to do it was just to identify the corner tiles without actually putting them together. And then in part two, it turns out they want you to put them together. But anyway, so I'll walk you through first how I did that. So I needed to match up edges with edges, and I went through a bunch of ways of doing this, but eventually I said I'll just represent the edge as a string. And so if it's this top edge, it'll be, that's the string. If it's this edge, it'll be the string going down in order. So top and bottom edges are always left to right, and left and right edges are always top to bottom, so that way if I have the left edge of this and the right edge of this, they will match if they match. And now we also have to, in order to match the edges, we may have to rotate and or flip. And so let's just go through how I represented that. So I said an edge is a string, and then so yeah, okay. So what I did is I said edge is a string, and then a tile is going to have four edges, and I decided to label them top, bottom, left, and right. So those will be the edges. Okay, so that's it. And then we have a picture, which is pixels, and pixels is just a list of strings. So that assumes that I've split this into characters basically. So the outer list is rows, the inner list is columns, and then you have one character. And so then I said I want to represent a tile, and so a tile is one of these things, and it has an ID, and it has a grid of pixels. So tile has a tile ID and it has pixels. And now one bonus of representing these things as immutable name tuples, immutable because the pixels array is not immutable, is that then I can basically do these flip and rotate operations and return a new tile. So that's what I did. So I said, you know what, if I rotate this tile, n is how many times I want to rotate it, I just say take the pixels and then n times. So rotate 0 will do nothing, rotate 1 will do this once, rotate twice will do it 2 times, and so on. I say here is a list that I'm going to stick the output in, and basically what I said is for each column ID, right? So to rotate it, I want to take the first column bottom to top and then turn that to be the first row. And the second column bottom to top will be the second row, right? So for each column, I say take the rows in reverse order. And so when C is 0, I'm going to take the first element of each row in reverse order, which is the first column going up, and then I turn that and that'll go across, right? And so on. So this is just turning it 90 degrees clockwise. And then I replace pixels with rotated, and then I do this name tuple thing where I say return self.replace with pixels and pixels, so that's going to keep that tile ID the same. Similarly, I have this flip horizontal, which returns a new tile, and all I do is for each row I just reverse it, so that counts as flipping it that way. And I have this do which is nice because I'm going to want to say, flip horizontal, not flip horizontal, and that way I can pass in true or false and make that happen. And there's a flip vertical that does the same thing, except it reverses the rows instead of the columns, and so on. And then what I want to do is I want to do, all rotations, which is basically saying what are all the tiles I can get by doing flips and rotations. And then as someone on YouTube pointed out, and then I also figured it out before they pointed it out too, if you do a horizontal flip and then a vertical flip, that's basically the same effect as rotating it twice. So you can get all the possible combinations without including both horizontal flips and vertical flips if you just do horizontal flips and rotations. Because if you, like I said, if you include a vertical flip in there too, then that's just adding 2 rotations and you've already accounted for that basically. So I say, to get all rotations, and it's just going to give me a bunch of the 8 tiles I can get from this. Either I flip horizontal or I don't flip horizontal, and I rotate 1, 2, or 3 times, and then I just yield that tile, not tile. Okay, so now for each tile, I have the 8 variations on it, right? And just to be helpful, I gave it properties for what is the top edge, what is the bottom edge, what is the left edge, what is the right edge. And what that means is that because flip vertical returns a new tile object, if I say flip vertical and then dot top, that will give me the top edge of the new tile. So that does what I want to do. And finally, there's this edges that so let me the second part was so involved that I've forgotten some details of the first part now. But anyway, so here's this function. I said I was going to add comments. Let me add comments. Rotate the tile clockwise n times and return a new tile object. Flip the tile horizontally and return a new tile object. And then obviously this one is flip the tile vertically. And all rotations is return the 8 tiles I can get from this one by doing rotations and flips. Okay, and then I won't label these top edge. And then this edges says I'm having trouble remembering why I even did this. Self-rotate 2.edges. So that's oh, I'm gonna have to read my code and see why I did that. But anyway, here's parsing, which takes the raw and returns the nasty tile stuff. And then this is another parsing function that takes the actual input that looks like this, splits it into things that can be parsed into tiles, and parses them into tiles. So this is like 400 lines of code. So this was a hard, involved problem. And so now I want to find corners. And so I want to return corners, and let's forget about the oriented, so they'd be the top left corner part. Okay, so now I remember. So returns the edges of the tile as strings. If reverse equals true, rotates the tile by 180 degrees first, which results in all the edges being in the opposite direction. So what do I mean by that? What I mean by that is like let's look at this. So here's this tile where that's the top edge and that's the bottom edge. Okay. Now if I were to rotate this twice, then the bottom edge would be this backwards and the top edge would be this backwards, and same thing. So basically the important part is that it takes the four edges and reverses them all as strings, which is what I wanted. So it's confusing, and that's why it's probably not a great design. And in fact, I don't think I ever used the fact that this is like a named tuple. I just use it as a list. But anyway, like I bet if I did okay, so yeah, I did that. Anyway, okay, good. So now I understand what I did. So find the corners. So first, what I do is I want to say count up all the edges, reverse edges that occur. And so what do I mean by that? For example, if a tile had the top edge A, B, C, D, and that's not the way the edges look, we would count A, B, C, D once and also D, C, B, A once. Okay, and so that's what the for reverse and true false for edge and tile edges reverse does. And you can see I'm just using, even though it returns this edges thing, I'm just using it. I'm just iterating over it as a tuple. Okay, so I get these edge counts that says, and so the idea being that, and this isn't guaranteed to work, but it turns out it does work, that I can identify a corner because it will have, so basically if I see an edge twice, that's a possible match, right? And if I see an edge once, that's not a possible match. So if I see ABCD only once and also DCBA only once, then I know that that edge has to be on the outside of the puzzle when they're joined together, right? And so now I know if a tile has two edges that have to be on the outside, it must be a corner piece. And so that's how we're going to identify the corner pieces. And so corners is a list of tiles, and no matches is NM. NM is going to tell me, I don't even know why I need NM. I think that's for debugging. Anyway, so what I'm going to do is I'm going to say for each tile, I want to find the number of edges that have no matches. Okay? And so I look at each edge, and if edge counts edge equals 1 and edge counts, this is slicing, basically it reverses a string. And so if I only saw this edge once, which must have been when I was constraining this tile, and I only saw its reverse once, then that's an edge for this tile that has no matches. And I don't think I actually need this NM. I think that was just for debugging. And so that's maybe I call this sides with no matches equals 0, sides with no matches plus equals 1, and I'll delete this NM since it doesn't seem to be doing anything. If sides with no matches equals 2, okay, so now I don't want to talk about why I want to get rotated this way. It doesn't matter. So just say basically what I said is, if I find a tile that has two sides with no matches, it's probably a corner. Um, and now that's not guaranteed to work, right? Because you could have a corner where, like, imagine that here's a corner square and the top edge is identical to two other edges that match somewhere else, right? Then in that case, you're not going to get this condition met. But it turns out in the data set they gave us, this condition was met. So if I have two sides with no matches, that's a corner. And I add them to my list and I return that list. And now so you can see there's a lot more stuff because there's part 2 is pretty involved as well. So now what I do is I say, take the raw input, make the tiles, corners equals find corners tiles. Maybe I should do assert that len corners equals 4, and this is what they say that those should be. So basically I can do the corners without really putting the puzzle together, just by counting the edges and seeing if they match. Okay, so anyway, that works. Let me make sure I didn't break anything. Yeah, so I didn't break anything. So that's how I identify the corners by finding, I didn't check that the two sides are next to each other or anything. But anyway, I found 4 corners and I multiplied them, and that worked. And so it says, now you're ready to check the image for sea monsters. The borders of each tile are not part of the actual image. Start by removing them. So in the above example, the tiles become this thing. And now you glue them together to form the actual image. Okay, so you already search for sea monsters. Because your image is monochrome, a sea monster looks like this. When looking for this pattern in the image, the spaces can be anything, only the pounds need to match. Also, you might need to rotate or flip your image before it's oriented correctly to find the sea monsters. In the above image, after flipping and rotating it, there are 2 sea monsters marked with O. They found these sea monster patterns. Determine how rough the waters are by counting the number of pounds that are not part of a sea monster. The above example, the habitat's water roughness is 273. Okay, so in order to do this, we need to put the puzzle together. Okay? And so again, putting the puzzle together in general is going to be a hard problem, right? But hopefully they gave us a nice input that works. And so what I said is I'm just going to start in the top left corner and then use pieces that are laid down to give me constraints on what has to be next, and then try and fill in those constraints. And so that's why my corners orient the corners so that it's basically the top left. So like in this corners code, when I found a corner piece, a side with no matches, I try each rotation and check that the left edge and the top edge are the ones that don't match, and that's the one that I add to my output. So I just keep, and obviously it has to be a corner, so I just rotate it 4 times, and one of those times will have the left edge and the top edge matching. So that way I can start the puzzle with one of my corners and go from there. Okay, and I want to assemble the puzzle, and I'm going to assemble it by basically making a grid of tiles, right? So, here's a tile, here's a tile, here's a tile, and so I'll call that an assembly. Maybe that was a dumb name. And now I'm going to represent a constraint. And what is a constraint? Says that the tile at location ij must have sides that match the specified top, bottom, left, right. Okay, and so he says so if I have this constraint, and I don't know if this constraint is satisfied by a tile. So I check if this constraint says that if this constraint specifies a top and the tile's top is not what this specifies, then that's false. If we say your bottom must be something and your bottom's not this bottom, it turns false. Left turns false, right turns false. And if none of those is the case, then this tile does satisfy this constraint. Okay, and so that's all for constraints. Let me just put a docstring. Does the tile satisfy this constraint? And again, if you had watched me for like going for 2 hours this morning, you would have seen me going through several designs for this that did not work. And then also, I decided that like when I had a lot of constraints, I wanted to pick the ones that were most restrictive. So I just wrote this num constraints function, which just checks, which just counts from, I guess, 0 to 4, how many of these top, bottom, left, right are actually specified. Okay. And so now I want to find the constraints. Okay, create constraints from partially filled in assembly. Okay, and so I just say n is the side length, and I just go over. So I iterate over this assembly, and remember that an assembly is a grid of tiles or nuns. So nuns are tiles I haven't placed, and tiles are obviously tiles that I have placed. So again, I use my double enumerate trick, and I say for I row for j tile, and it looks like I don't use tile, but whatever. And so if this tile is already filled in, then I don't have a constraint on this square because it's already filled in, so I don't need a constraint. The constraint tells me what I can put there. And otherwise, I'm just going to make a dictionary to keep track of my constraints. And so I say, if this location is not in the first row, and if the neighbor, which is the location above it, is filled in, right? So I use a walrus to get it and assign it to neighbor, and I'm checking it as a bool. So if it's none, that'll be false. So if the cell above me is filled in the assembly, then I have a top constraint that I must match the bottom of that neighbor. If there is a neighbor below me, then I also have a bottom constraint that the bottom of this has to match the top of that. If I have a neighbor on the left, then there's a left constraint that must match the right of that neighbor. And if I have a neighbor on my right, then I have a right constraint that I must match the left of that neighbor. And now, so constraint at this point will either be an empty dict or it'll be a dict of some things if any of these bit, right? And so if it's not empty, then I'm going to say I'm going to create a constraint at location ij with these constraints, which will be top this, bottom this, whatever. And if there really are no constraints applying to this cell, then I'm not going to return a constraint because I don't have a constraint. Okay, and so this is how I find all the constraints that apply to a location. And now no constraints for already filled in tiles or unconstrained locations. Okay, so now I assemble the images into a list of tile, which is an assembly. So take the tiles and figure out how to stick them together. Okay, and so I start off by finding the corners. Okay, so try each corner. So what do? I make a copy of the original tiles because I'm going to modify them. And now I want to create an empty assembly. And I want to put this corner tile in the top left. And finally, I want to keep track of which tiles I've already placed. Okay. So at this point, I've only placed the corner. And now what I want to do, and I think this for loop was like overly defensive, so I probably don't even need to do that. Like, I could probably do, let me change this to just pick a corner and see if it works. Tile equals corner 0. And I probably don't need this. Okay, so that's okay. And now let's fix this. Pick a corner, any corner. And I don't think I need to do this either. I think that'll still work. Yeah. Okay, good. Create an empty assembly. Put this corner tile in the top left. Keep track of which tiles I've already placed. Okay, and so repeat until all tiles have been placed. Okay. Just care about unplaced tiles. Find the constraints based on all the tiles placed so far and order them by descending number of constraints. So the idea there is that if I have a constraint that specifies 3 sides, that's going to be much easier to fill in than a constraint that only has 1 side. And so I just want to consider those first. And did I find tile to add so we can break out of inner loops? And now try constraints one at a time and see if we can find a tile that satisfies them. So for the constraints, and then I iterate over all the tiles, which is only the unplaced tiles. If tile ID is not in place, and because I did tiles not in place already, that seems unnecessary. So let me do that. Let me see if that works. Yep, that's still okay. So I take the tile for each tile, and I try all rotations, which is the 8 tiles I can get from this one. And if the constraint is satisfied by that rotation, then try all rotations for this tile. And if the constraint to see if any satisfies this constraint. And so what do I want to do? Place this rotation, which is a tile, at ij. And now, so what I do is, like, let's say I have a tile with ID 10, right? Then this all rotations is going to generate a bunch of other tiles with ID 10. And I'm going to take one of them and then stick it in the assembly, and then also this placed. And so now that's actually different from the one that was in my tiles list, but that's okay because I am going to, up here, I'll remove the corresponding tile because its tile ID would be in place, so it doesn't really matter. And so then, you know, once I find this constraint, I say, yes, I found one. I break out of the rotations, and now because I found one, I break out of the tiles, and because I found one, I break out of the constraints. Yes, that's terrible and nasty. And then I return the final assembly. And so that works because of the actual inputs we got, but it's also, you can imagine some hard inputs for which you'd have to do something more complicated. But I mean, not that this is not complicated, but this is a very naive approach in that it's place a corner tile and just like start satisfying constraints. You can imagine a set of tiles for which that naive approach wouldn't work, and you have to do something even harder. So finally, so this says, given some tiles, I'm going to stick them together in an assembly. And now remember, an assembly is a grid of tiles, and now we want to glue them together by removing these edges, right? And so what I do is I say big N is the number of the side length of the assembly, meaning the number of tiles, and little n is the side length of each tile. And then what I'm going to do is I'm going to remove 2 from, I'm going to remove the left side and the right side, top side, bottom side. So that's going to give me little n minus 2 pixels to add from each one. And so the dimension of the output is going to be n minus 2 because I remove the 2 sides times n. And what I do is I just make an empty 2D grid full of empty strings that has the right size. And then again, my double enumerate for I row and enumerate assembly, for J tile and enumerate row. And again, the tile is actually a tile. I do this crop trick where I say for each tile.pixels 1 to -1 says remove the top row and the bottom row, and then for each line in that, I want to do again 1 to -1, which removes the first element and the last element. So that has the effect of getting the inner n minus 2 by n minus 2 square. And now what I do is I just say I want to for the index and the cropped row and enumerate cropped, and for the J index and the pixel and enumerate cropped row. And then this is fiddly, but it's the ith grid, so I times n minus 2 plus ig. So I set the pixels in the glued thing and I return the glued. So I've glued them all together. Okay, so now I am at the stage where I have removed the gaps and formed this actual image. Okay, and so now I need to search for sea monsters. Yes, this problem never ends. Yes, this problem is hard. Yes, this problem took forever. Yes, yes. So what I did is I pasted in, the raw image of the sea monster, and then I just converted it into a list of coordinates that I can use with an offset. So I'll say, again, double enumerate. There's tons of double enumerates here. I take the sea monster, split it in new lines, and iterate over it, and I say if at each ij, if you see a pound sign, then you want the tuple ij. Okay, so now I know where the sea monster is. And now I'm going to find sea monsters in some pixels. And remember, a pixel is just a list of strings, so a grid of strings. And what I'm going to do is I'm just going to say add a doc string here. Glue together the tiles into a single grid of pixels, removing the edges of each tile. Okay, and so now this is offset for a sea monster. So now when I have these pixels, I'm going to return the indices of the top left corner of each sea monster. And so here I just do the brute force. And so for I row and enumerate pixels, for JC and enumerate row, So I have these coordinates, and I'm not using C again. It's probably um, funny story. In the first edition of my book, um, I did this basically and ignored the C as a way to get the indices for a row. And someone actually opened a Stack Overflow question that was like, "Why is Joel so stupid to do this?" Like literally, that was the Stack Overflow question. Why is Joel such an idiot? He did this in his book, and so here I'm an idiot again because I'm doing it again. I'm doing JC in enumerate row instead of 4J in range len row, which I could have done, but I'm an idiot, so I did 4JC in enumerate row and didn't use C, so whatever. So this gives me every IJ in the grid, and I didn't want to do boundary checking, so what I did was I did try except index error, and of course if I try and index outside the grid, I'll get an index error. And so what I check is that every time I do pixels top left plus DI, top right plus DJ for DI, DJ being the offsets in the C monster, then basically, the C monster will say, 0, 10, 1, 0, blah, blah, blah. So it says these are the offsets, and I just check every offset from IJ, just check by brute force, is this a pound? And if it is a pound, then we have found a C monster, and so I yield that. And if there's an index error, that means I tried to go off the grid, and so I just continue because that's not a C monster. Okay, and so finally, roughness is count the pounds that are not part of a C monster. God, this problem is long and hard. All right. So this is a little bit of a hack, but put the pixels in a tile so we can use tile methods. And because it says, after flipping and rotating to the appropriate orientation, there are 2 C monsters. Okay, so we're going to have to try all those. And so what I want to do is I want to say, for each of the 8 rotation flips, find the list of C monster top lefts. Okay. So for each of those 8, it says find all the C monsters you can and convert it to a list because it was an iterator, so we need to do that. And now only keep the ones that had C monsters. Hopefully, only one of them had C monsters. And that's our tile and C monster locations. Okay, and so now, again, now we can compute all pixels that are showing a C monster, and C monster tiles. These are not tiles. These are C monster pixels. And count all the that are not C monster pixels. Okay, so that gives us the roughness, and that returns it. So now you can see in the unit test, tiles equals make tiles raw, corners equals find the corners, assert that I found 4 corners, and assert that the product of the corner IDs is what it's supposed to be. For part 2, I didn't actually need this, so I can take it out. And now what I want to do is I want to assemble the image, which will give me that assembly object. Then I glue the images together to get some pixels and assert that the roughness of the glued is 273, which they told me it was. And so now I just do the same thing using my inputs, which is a lot of tiles. And I make the tiles, I find the corners. Again, I assert that there's 4 of them, print their product, assemble the image, glue them together, and print out the roughness. And let's make one last check that it works since I made some changes, and it works. Okay, so that was a terrifically involved problem. It's possible there was a simpler way to do this, but my guess is there probably wasn't. And in fact, one thing that I looked at was sorry, leaderboard I think was what I meant to show you. If I look at the leaderboard on 20, it's really interesting, right? So the first star, the best people got it in like 4 minutes. So obviously it took me a lot longer than 4 minutes, but more power to the people that made them in 4 minutes. And then the best person for part 2 was 25 minutes, so like more power to that person. And then once you get down to like 13th place, it's already 40 minutes. And if you'd finished part 2 in an hour 13, you would have been still in the top 100. So like there's a lot to do in part 2. So there's probably not like a trick that would do a lot less than this, but this was involved and hard. And look, it took me 40 minutes just to explain my solution to you, let alone try and solve it. So yeah, hopefully that's the hardest problem of the whole Advent season, because I probably spent at least 3 hours on it plus another 45 minutes just explaining it to you again. So I'm satisfied that I got it, but that was a lot of time. All right, cool. So I will probably do day 21 tonight. So I'll see you